The device we need is a safety valve. This is a huddling chamber safety valve. Like the relief valve we saw earlier, a safety valve consists of a valve body, or casing, which forms an inlet and an outlet for system pressure to flow through. It also has a disc, sometimes called a feather, and a seat, which in this case is a replaceable seat bushing. The disc is held against its seat by a spring. The lift of the disc is guided by a disc guide and a spindle, which is attached to the disc and runs through the center of the spring. Unlike the relief valve we saw, this safety valve has two spring washers, one above and one below the spring. These hold the spring in place. A spring adjusting screw controls spring tension, and a lock nut holds the adjusting screw in proper position. So far, this safety valve is almost identical to a relief valve, but a safety valve has some parts that a relief valve may or may not have. First, there's a release nut at the top of the spindle. The release nut is part of a hand lifting assembly, which includes one or two lifting levers. Each lever is connected to the valve with a pivot pin. For testing the valve and for making certain it is clear of any obstructions, the levers are raised. The levers, in turn, push upward on the release nut, lifting the spindle and disc. The valve closes again when the levers are lowered. The hand lifting assembly and top of the spindle are covered by a valve cap. A big difference between a safety valve and a relief valve is the shape of the disc. Notice that the disc or feather of a safety valve has a lip which is not exposed to system pressure when the valve is closed. Notice also that there is a small chamber called a huddling chamber just below the disc, and an adjusting ring that's threaded onto the outer edge of the seating area. The adjusting ring is prevented from turning by a ring pin that protrudes through the wall of the valve body. Now, let's see how these components work together. The pressurized fluid, usually gas or steam, is always in contact with the center portion of the disc, called the pressure sensing area. Again, let's assume that normal system pressure is 18 psi and that the valve is set to open at 20 psi. At 19 psi, nothing happens, but at 20, the disc or feather begins to lift off the seat. Suddenly, the lip of the disc, which wasn't exposed to system pressure, is exposed to system pressure. Because a larger area of the disc is exposed, there is more total force being exerted on the disc, even though system pressure remains the same. The increased force causes the disc to pop open to about 60%. Two forces hold the disc in this 60% open position: system pressure and the velocity of the escaping steam striking the disc. If system pressure increases further, the velocity of the steam also increases, and the two forces will lift the disc even higher. What does the initial popping of a safety valve accomplish? It instantly gives overpressurized gas or steam a wide escape route. The wider the escape route, the less velocity the escaping fluid has. By reducing velocity, the popping action of the valve minimizes the steam cutting that can result from a high velocity flow of steam. So, now we know that there's a major difference between the way a relief valve opens and the way a safety valve opens. What about a difference in the way they close? Again, here's our safety valve, still in its fully open position. System pressure begins to decrease, and along with it, the velocity of the steam. Spring tension begins to regain the advantage, pushing the disc downward. Now system pressure is at the point where the valve first opened, but because the lip of the disc is still exposed to system pressure and steam velocity, the valve remains open. Only when system pressure drops below the set point of the valve does the valve snap shut. The valve snaps shut instead of closing gradually to abruptly cut off the flow of steam, thereby minimizing steam cutting. A small cushion of steam trapped in the huddling chamber prevents the disc and seat from slamming together hard enough to be damaged. Now that we've seen the basics of how a safety valve operates, let's go back and watch the operation in greater detail. As we do, we're going to learn a few new terms: popping pressure, simmering, blowdown or blowback, positive seating, and chattering. We're also going to explore the purpose of the adjusting ring that we mentioned but never explained. Once again, here's our safety valve. System pressure is normal now, and the valve is adjusted to open at 20 psi. 20 psi, then, is said to be the popping pressure of the valve, the pressure at which the valve will pop open. System pressure increases. When it reaches popping pressure, the disc rises off its seat, but pressure hasn't had time to act on the lips of the disc. This condition, where the disc has lifted only slightly, is called simmering. Usually, simmering lasts only a split second until system pressure acts on the lips of the disc, and the valve pops open. System pressure continues to rise, then levels off, and begins to drop. Even when pressure drops back down to popping pressure, the valve remains open because the lip of the disc is still exposed to system pressure and steam velocity. Only when system pressure has dropped below popping pressure is the spring able to shut the valve. When the disc is firmly in place against its seat, we say that the valve has positive seating. Positive seating is important to ensure that there is no leakage. The difference between the popping pressure and the positive seating pressure is called the blowdown or blowback of the valve. In our example, the popping pressure is 20 psi. Positive seating occurs at 19 psi. So the blowdown of the valve is 1 psi. Why is blowdown important in a safety valve? Well, let's consider a case where the popping pressure is 20 psi and the positive seating pressure is also 20 psi. When pressure reaches 20 psi, the valve simmers and lifts and continues to rise as pressure increases. When pressure drops back to 20 psi, the disc returns to its seat. But because 20 psi is both seating pressure and popping pressure, as long as system pressure remains at 20 psi, the valve can't make up its mind whether to remain closed or pop open again. In this situation, the disc is likely to jump up and down on its seat until pressure either increases enough to pop it or drops enough to give it positive seating. This up and down action is called chattering or machine gunning because of the sound it makes. Chattering is a serious problem. It can severely damage the disc and the seat. Blowdown prevents chattering by ensuring that popping pressure and positive seating pressure are different. Just as the popping pressure of a safety valve can be adjusted by turning the adjusting screw and increasing or decreasing spring tension, blowdown is adjusted by changing the setting of the adjusting ring. We can see how the position of the adjusting ring affects blowdown by studying what happens when the valve is closing. Remember that the position of the disc is determined by both the amount of system pressure and the velocity of the steam striking the disc. The adjusting ring acts like the nozzle of a garden hose. In a raised position, it directs the escaping steam right against the disc. Because most of the steam is aimed at the disc, the velocity of the steam exerts a large amount of upward force. Because of this added force, system pressure must drop well below popping pressure before the spring can force the disc back onto its seat. Raising the adjusting ring, then, increases the blowdown of the valve. Starting once again with the valve in its open position, let's lower the adjusting ring and see what happens. Without the ring directing steam at the disc, much less escaping steam strikes the disc on its way to the outlet. As a result, the velocity of the steam exerts less upward force on the disc. Because the system pressure is getting little help from the escaping steam, it takes more system pressure than before to hold the disc open. With the adjusting ring in this position, the valve will close against higher system pressure than when the ring was raised. As a result, the blowdown of the valve, the difference between popping pressure and positive seating pressure, decreases. As a general rule, then, the higher the position of the ring, the higher the blowdown. The lower the position of the ring, the lower the blowdown. To get a better understanding of one-ring huddling chamber safety valves, read through Section